Okay, what I think I'm just going to do is take a second shot at the kinetics chapter because I think I went too fast and I think I lost everybody. So forget your confusion from all this kinetic stuff. I'm going to start over on the chapter and I'll go a little slower and be a little more clear about stuff. Starting at the very beginning of the chapter, from the standpoint of this example, I'll just start here. This is something that's kind of simple that you can take this and you can just write it down. I would encourage you to learn it this way. So looking at this, the relationship between these rates is 1 over, I'm going to put a 4. And then the way it's usually written is this, referring to NH delta t, lowercase t, this is time, equals, I put a negative sign because it's on the left side. I'm going to put another negative sign. So that equals, now I'm going to do this one with a negative sign, 1 over 5. O2 and delta t. And now without the negative sign, 1 over 4. Delta. I want to keep this neat. And then that equals one more. Surely you could do that. I gave you a reaction, you could rewrite all that. Right? And I don't mind giving you the general equation for that, but just as a process, this is where to start. That's actually all there is to 12.1. But let me tell you that I think this is easier to work with. If you do it like this, I'm going to bring the -4th over a little bit. -1/4. 1/4. I think I'll just put it in parentheses. This part, I would tell you to write it like this. Some numerical value, and then the units are moles per liter to the -1, per second to the -1. Actually, it could be second, it could be minute, it could be hour, it could be days. It's going to be some kind of time unit. There's another example we'll come to later where that's hour, the units, and then I would write this term. I would think of like that. You have this coefficient out in front, you have the numerical value, you have the units, and you have the weight. So that's the way I think of all of these. You've got numerical value, and these kind of go together. These are the units, and that's the weight telling you what it's referring to.
So just to be clear, the fractions of the products are always negative, and the reactants are always positive.
Fractions of the reactants are always.
Oh, right, sorry.
Yeah, you throw the negative sign in for these.
Yeah.
And then these don't have the negative sign. Okay. So if you can do that, numerical part, units, NH3, then I think this next one comes off the page much easier. Of course, I only wrote the first one, but I could have put an equal sign and continued and written the rest of it as well. So 12.2, this is where you actually solve for something. 12.2, and the reaction in this one, we give you this reaction, There's the reaction. And you would write -1/2 delta concentration of H2O2 delta time equals, so now we're on the other side of the arrow, so I'm not going to put the negative in there. 2. I forgot the delta. Delta T. I'm still going to put 1/1, even though this is just a 1. So if you can get that far, that's where you start. The problem also says this. The problem mentions T equals 11.1. I won't include those in the ones I ask you, because this is an instantaneous rate. It's saying this is the rate at 11.1 hours. So we're going to be in hours this time. But just realize that it's kind of a red herring. What they tell you is the rate for H2O2 is 10 to the -2. And of course they put the moles in there. Let me go over that. Rate for H2O2 is 3.20 times 10 to the -2. And they wrote the units this time as mole per liter per hour. But that's the same thing as mole per liter to the -1, hour to the -1. Which is the same thing as moles per liter per hour. Those are all the same, they're just different ways of writing it. Just to keep it clean, I'm going to keep writing it like this. And then it says, if that's true, what is the rate for the other two? H2O and O2. That's your question. And that's what it's given. So I'll tell you first to go, okay, let's just do H2O first. So we've got these two things equal to each other, and I'll ignore this one for now. And again, I would tell you to go -1/2. They include they write it like this explicitly, and you see the negative sign there. So that is important because where was that? So first thing I want to do is turn this into -1/2, and then I'm going to change this into some numerical value, moles per liter, hours to the -1, and then my label H2O2. So I would turn this term into this first. And if I put the negative on here, then I have 1/2 negative. essentially this. And since this is equal to this is what I'm going to write in here. I'm dropping the negative in. I've still got a 1/2 out here. So basically all I've done is I've replaced this with this. And it makes the negative drop out. I'll replace, hold on, to make it more clear. If I take this and I take the 1/2 out here, and I go negative, all I've done is take the negative and put it in here and put that 1/2 out here. And you see that this and this are exactly the same. So I'm just going to rewrite all of this in there. Just come down. So the rate for the H2O2 I'm again making this more complicated. Sound more complicated. Moles per liter per hour. I suppose I can do this. You see what I've done? Instead of writing it like this, it's probably easiest to write it this way the first time. But just as a transition from there to there, I might be warming up now. So that's this term with the information they've included. And that equals, now we're going to write this term, and I'm going to go 1/2, and I'm going to turn all of this into the way I said it before, numerical value, mole per liter per hour, H2O. And I've got this, if I get the parentheses the same, I've got this. Hold on. They left this off. They should have as the label there. And over here I've got 1/2, some numerical value, mole liter hour, and now H2O. So again, I'm saying turn that into 1/n, some numerical value, mole per liter, I'm going to say second, whatever, and then label A. This is easier to work with math-wise than that is. Have I lost anybody yet?
What happened to the negative?
If this equals this, and I take this, and I stick it in here, the negative is gone.
Okay.
The negative is just kind of part of that general definition,
Okay.
because rates kind of don't make sense if they're negative. But the negative goes away. Anytime you get to here, the negatives are going to be gone. And I would change my parentheses here to go numerical value with the coefficient. Here's all my units, and this is my label. Coefficient and numerical value, all my units, and the label. If you can get set up there, the rest of this, I promise, is easy. So if you're lost at this point, ask.
What are you doing in the top right again?
That's just a general form I'm telling you. This is what the book tells you, this form, and I'm telling you to take this part and turn it into this. No, this. You've got that fractioning part that came from the coefficient from the equation. I'm saying turn all of this into this. The deltas are where the numerical value comes from. The A is where the label comes from. And the rest of it here is saying the concentration, that's the moles per liter. And the delta T, that's the seconds. And I'm telling you to turn that into that when you run it. That's what I've done going from here down to here. This is the numerical value they gave us. So that's what ends up here. If they give you a numerical value, it's going there. Which is what all these problems do. They'll give you that numerical value for one of the things in the reaction, and then you relate that to another one.
Why do you leave the moles per liters per hour for H2O to like have that value?
Leave it what?
Like, why are you leaving moles per liter per hour if you have 3.2 times 10 to the -2? Like, isn't that the value for that? Like the moles per liter?
Well, these two things multiplied together is the value that goes with these units. That's the numerical part, that's the units, and that's the label.
Okay.
Did I answer your question?
Like, kind of. I just like confused like why you need it there.
Why you
Anything
need
for just like the units.
why you need that there?
Like, why you need the moles per liters per hours if you already have that value and you're not going to solve it?
I am about to drop them away.
Oh.
But usually when you do math in these situations, I mean in chemistry, you keep the units and you keep the label. You always keep your units, but I am going to drop it off right here. So let me put it this way. If you can get to this point, the rest is very simple algebra. What you do is you just take the numerical part, 3.2, 3.20 times 10 to the -2. And now I'm going to say equals. I'm going to keep this numerical part equals 1/2 that. And that's what you're trying to solve. You just get the units out of your way. It is H2O we're working on, so the units, all these units really do go here. It's the labels that make this not seem equal to each other. And I'll even say this, if it looks better, X is what you're solving for. You're solving for that. That's what X is. You with me? Multiply both sides by 2, and you get equals X. And ultimately what this means is this part equals, the algebra isn't always quite that simple, but I'll do another one. And then moles per liter per hour, and here I put H2O. That's really what you just saw. And this is my notation, even though it's real and it works. The book and probably the ACS test is going to say, I think what they usually do, what the mistakes I see, they leave the label off. I don't know why. But I think the label should be there. Okay, let me just do another one and see if it sinks in. You've got to check your learning one. I will always give you the equation. This check your learning one for 12.2 doesn't give you the equation. The equation is up there in the chapter. just says decomposition of NH3, but that's, and I will always give you this, NH3 down to N2 plus H2, balanced. 2 of those, 6 of those. Let me just make sure. Before I waste our time. Here. 2 of them. Camera's still on, okay. And this one says, okay, here's your reaction. And it says for rate 4. They also say the reaction is 1150 K. That's a red herring, just like the 11.1 was in the other one. So I won't be doing that. Is moles per seconds, which is the same as moles liters to the -1, seconds to the -1. And then it says, okay, what is it for, what's the rate for N2, rate for H2. That's what it's asking for. And we'll do it exactly the same way. So it gives you one of the rates, and then that general equation is what relates them all. Since the negative goes away, I would tell you to do that relation like this. 1/2, and this is the NH3 I'm doing, so I'm going to use this for my numerical value. So there's my numerical value. Next is units, mole per liter per second, and that equals, and then for, if we're doing nitrogen, some numerical value, I could write this as an X at this point, but some numerical value, and then mole liter second. I'll let the label off. I can't complain about them leaving the label off if I'm going to leave it off. I've got to put it in. 1/3. So I'm just doing this positive now. It eliminates any confusion about that negative. 1/3. This is the value I'm looking for. And then moles per liter per second. And this is for N2 equals. So I kind of skipped that theoretical step. You guys with me?
Where'd you get the 1/3 from the MC?
Oh. Yeah. Yeah. You guys with me? And the rest is just this. To solve it, I would say leave the units and labels behind. Put an equal sign down here and go 1/2 2.10 times 10 to the negative, is it -6? Yeah, it's -6. -6, -6, -6. 1/1, and let's turn that into X. And of course, this one's very easy. If you do this math and X equals whatever this is, half of this is 1.05 times 10 to the -6. So if you just divide that by 2. So what that means is the rate, 105, the rate for, which one am I doing? That's the answer for N2.
So no matter what sign we get, like negative or positive, if it says the rate of production or the rate of decomposition, it's like decomposition, it's gonna be negative.
Theoretically, that theoretical equation is negative, but really it goes away. I mean, in this one, NH3 is on the left, and they gave you this without a negative on it. You get to forget that whole crap about negative. You just take it as they gave it to you and you go on. You put the negative sign in that theoretical equation because that's what's disappearing, and that's the only way you could, but that negative is there to turn a rate into a positive rate. I don't know how else to explain it to you, don't worry about it. Just go here, take what they give you, and forget about negatives. There's a lot of heavy theoretical stuff here that it's almost like if you took an upper level chemistry course, it would probably be in physical chemistry, I think, or maybe inorganic, wherever they do kinetics. And at the end of all that, then all this would make sense. But since 1152, they just kind of throw it at you. So you're stuck that way for a lot of stuff this semester. Where these equations comes from is pretty high level stuff. If you had some background, if you had some background in calculus, and B, you were really comfortable with all that calculus, then that next stuff I was doing last time that I was losing y'all on would be a lot more obvious too. But we're not going to do this from that standpoint, so I'll give you equations to work with, and you just kind of have to plug and chug and not try to interpret everything you're doing. All right, the next one is let's do it for H, H2, and H2. Now I'm going to do the 1/3, some numerical value, moles, moles per liter per second, and now it's H2. And again, I'm going to leave the units and the label off, and I'm going to bring this down. Numerical value, but let's make that an X now. You solve for X, and that's the X that goes with the H2. Algebra-wise, I'm going to multiply both sides by 3. And that's going to be the answer. So it should be 6, 3 divided by 2. I didn't do that in my head, I cheated. I tried to do it in my head. That's what you get for H2. So to write it properly would be 3.15 times 10 to the negative 6 mole per liter per second. Now I would always put the label on H2, rate for H2. You could say rate for H2. So that means moles per liters per second. And just so it's a little more. Moles per liter is a concentration, molarity. Moles per liter. So this is how the concentration is changing per second. It's a rate of change of the concentration.
Could you just multiply 1/2 by 2.10 times 10 to the negative 6, and then just divide it by 1/3?
You could, divide by 1/3. That works too. I multiplied by 3, and then I multiplied 3/2 by this. You would do that's more intuitive to you. Divide that by 2 and then divide it by 1/3. That's fine if you want to do it that way. That made my brain go, oh, really? That's the way you think of it? I do it in step-by-step algebra. So, everybody okay with that? Okay, I've got. Let me see. Let's just take a minute and see how you're doing. This is what do you call it? End of chapter problem number. I lost it. Might actually have to look at the book. Let me get it written. So they give you this. BR negative. They have aqueous here, which you're supposed to, but all those designations don't change anything for what we're doing. So I'm not going to put aqueous there. Plus BR over 3 negative 6H plus. You remember net ionic equations from last semester? I know my class did. That's what that is. It's a net ionic equation. That's why you're seeing negatives and ions. But it doesn't change anything that we've done. And they tell you BR negative, that's this with the 5. BR negative is 3.5 times 10 to the negative 4. And this one is in seconds. Moles per liter per second. And then, of course, it asks you for one of these other ones, BR2. I haven't worked this one out yet, but I think it'll be fine. First thing to write. Oh no, I want to see if y'all can do it. What's the first thing you're going to write?
Negative.
Yeah, but drop the negative out of this
Oh,
one.
yeah, so you just do that.
You just take this as they give it to you. Second equals what? Oh. 1 over 5. And what do I write over here if I'm looking for BR? Gotta go 1 over 3. I could go ahead and just say X. You could solve that, right? Oh, I didn't write my labels. Maybe I can't give them too much crap. Multiply both sides by 3. That equals X, and if I had my labels here, this would all be here. Three times 3.5 divided by 5. Let's see what happens. The way I do it is my calculator is go 3 times 3.5 divided by 5. It gives me 2.1. So that's what goes in for X. And then the units are. I suppose if you say rate for BR2, then you can get rid of the label. I just think the label ought to be there. Especially when you're working with math, you know it. That variable. Okay. You guys all right? There's another way to do these that I could see into and y'all couldn't. There's an algebraic way to do it instead of just inspecting the data like we were doing before. Example 2, 4. And I'm going to write all the data here. Trial. Here's the reaction. 3. That's the reaction. Okay, concentration of NO. Concentration of NO. Concentration of O3. I should have said this first. You remember this? The overall rate is a rate constant times something, and we'll just call this M, B, in this case. So these are always the reactants. So in our case, the rate, concentration of NO to M. And this is where I lost y'all last time. So this is the question where what is the rate? Rate with respect to A. Rate with respect to A is K. And then the overall rate is expressed this way. And trust me, the theoretical walk to this, again, is just, we're not even going to go there. It's not 12-12 type information. These are the order, reaction order with respect to A. Respect to D. And you add them together. I don't mind giving you that and that and that, and maybe even that reminder on the test. But exactly what this stuff means kind of gets pretty heady, so. All right. So I will say, let me leave over here. So for this reaction, you could go ahead and write that down in theory as soon as you see this, because those are the two reactants. And that's always true. The general equation is always this. What we're looking for now is the M and the N. And we're given a bunch of data. They give you the rate for NO2. Those are the headers. So there's always going to be a rate here, and these are just integers. And just give me a second to write all this in. is right, -6. 10 to -6. This one goes. I know for a fact I lost y'all right here. Okay, that's the data. And now the question is, what is the order with respect to NO? That is, what is M, what is N? That's what we're being asked. Okay. There's an algebraic way to do this that's not very hard, but first we can simplify this a lot. You see how these are all 10 to the -6? These are all 10 to the -6. We can just go, because they're all proportionally, let's just erase them. They're all 10 to the -6, so I'm going to get rid of all of them. And let's just deal with them. And since it's 0, 0, let's just do this as well. 36999. These are all 10 to the -6, and they're all 0, 0, 0. Let's call them 1, 1, 1, 2, 3, 3. That simplifies things a lot. Over here, this 6.6. 8.694. Okay. -4, -4, -4, -5. Let's move this decimal back once. So we have 0.660 times 10 to the -4. And then we have all -4s. You with me? So I'm going to put this here. 10 to the -4. 0.660 times 10 to the -4. And now we can do it again. Let's get rid of, I won't get rid of everything, but I can at least get rid of the 10 to the -4. That simplifies things a lot. Okay, now here's the algebraic trick. I'm going to do trial 1 and 2 here. Concentration of NO. I've got it right here. So I'm going to do NO first and NO and O3 second. So NO is 1 to the M, and O is 3 to the N. I got those from 1 and 2. I have rate 2. This is rate 1 and this is rate 2. So now I'm going to do 1 and 6. Six, 2, okay. You see how I got those? I just took trial 1 and 2 and I set this up. And actually the rate for 1 is this. So I'm going to put 0.660 here. And the rate for 2 here. There. You see how I set that up? This, now we can solve for orders. rather than inspect the data and say, this times this is this. One of the keys here, though, is I chose one of these, a pair of these. I could have done 1 and 3, I could have done 2 and 5. I chose these two because NO is constant. So what they did is somebody came in and did a trial. They did this concentration of NO, this concentration of O3, and then they found that NO2 changed at this rate. And then they cleaned up, started over, and did another trial, and they mixed it in these proportions. This concentration of NO, this concentration of NO3, and then they found the rate was 1.32 for this. And then they cleaned up and did it again. So this is 5 trials. But they purposely did a couple of them the same and these different. And they did these the same and these different. They didn't have to do 6. They could have only done 4. They could have, as long as one of them is constant and one of them is changing, one of them is constant, the other one is changing, then they've done what they need to. Most of the problems you'll get on this will only have 4 data points, or maybe even 3. But the 1 and 2 I chose because these are the same. And now notice, no matter what, so K is the same here, and the N's are the same here. And if that's true, those cancel. That's why I made sure at least one of these was the same. And I'm going to do the same down here, except these will be the same, those will be what cancel. Truthfully, I shouldn't have those in brackets. I should have them because those doesn't mean concentration of 3. That is the concentration of 3. So really what I should have written here is I should have written them like this because they're not concentrations now. It's the answer to the question of what is the concentration. I really should have written it like that. So the concentration equals this, and I just put it in parentheses. The concentration equals this, and I just put it in parentheses. See what I mean? So now this was 2, this was 1. All right. So these cancel. And we're left with, we can go ahead and do that math. 0.660 divided by 1.32. I get exactly 0.5 equals should have it in there. This equals to the n. Just a mathematical fact. So I can rewrite that as, and now I can solve for n. What is this? It's 1/2, aka 0.5. So what must this be? Yeah, let me do that. Let me write the 0.5 as a 1/2. So now it's obvious what n is. N has to be 1. So we got 1 out of them. No, wait. We kept NO constant, so what we just found was, and we kept n, so we solved for n, so it was this. So that's a 1. So it's first order with respect to O3. And now we can do the other one. This time, let's pick one of these. Trial 3 and trial 4. Concentration of NO is 2. M, concentration of O3 is 9. Do it again. Four. No, this is 3. Whoops, that's 3. And that's 4. Now, that cancels out. Rate is 3 and 4, 1.98. 3.96 for 4. 1.98 divided by 3.96. My calculator says 0.5, but I know this is more satisfying if it's in 1/2. The K is still there, but ignore the K. And again, we find out this is 1. There's one more step to this problem, but you see how I did that? So we just found out the orders of reaction.
Can you give a refresher on what imminent means?
That's all that theoretical crap that I'm telling you that's not going to help you at all. It's a long walk to tell you. This equation, how this relates to those rates that we were talking about before, is a long walk. So anyway, you just kind of have to take our word for it. You have to take our word for it that this equation dictates the rate, denotes the rate. Before we were given a rate, and we related rates to each other, this one was an experimentally determined rate of the product, and then we were able to find the order of reaction this way. But kinetics is a much bigger subject. This is honestly just dipping your toe into kinetics. So this is what we found out. The last question is to find K. If you find K, you can pick any one of these you want. I'm not sure any one of them makes it any more simple. Let's just pick one. Let's just use number 2. I chose that. I could have used any one of them. The rate here is 1.32 equals K. The concentration of NO is 1. So NO to the first power, concentration of, oh, you know what? Now I got to put all those powers back in. What was this? -6. And this was times 10 to the -4, I think. Let me check. Yeah, -6, -6, -4. Okay, so we have to have that there. So using number 2, the rate is 1.32 times 10 to the -4 equals K. It's this concentration to the first power times this concentration to the first power. And now we solve for K. I think the easiest thing to do is multiply these first. But you can do this with algebra however you like. More than one way to go. It's going to be 6.00 times 10 to the -12. Because you add the exponents. Right? And now it's K equals. I'm not sure if those calculators give you an easy way to use the scientific notation, but I'll show you the way I would solve this. I just split it into 2 pieces. And this I do with my calculator, and this I do with just the way you deal with those exponents. The numerical part, well, they're both numerical. The part that is in powers of 10, 1.32 divided by 6.00 is 0.220 for my significant figures. My calculator just said 22, but that's three significant figures, that's three significant figures. When you do these, first thing to do is take this and bring it up to the top. When you bring something from the bottom to the top, you change the sign. So in this case, I'm going to do times 10 to the 12. 12 minus 4 is 10 to the 8. The units here, that's what I'm going to explain to you next. What is the overall order? An order with respect to NO, that was 1. Order with respect to O3, that was 1. But what's the overall order? You just add the exponents. Yes, the overall order is 1 plus 1 is 2. I'm going to peek to make sure I get the right. There are units that go on K. I could go through the algebra. So this is second order overall. So you end up with, if I put liters, do that right. There's a little chart in the book I keep keeping at, so I don't have to do all the algebra. Liters per mole per second. Liters per mole per second. So the units do matter. You put them on there. But how I got them, what the units are going to be for K have to cancel out whatever's here to create moles per liters per second over here, because that's what a rate is. An overall rate has to be moles per liter per second. So if this was squared, it would change things, and I need to have the right units here to make it cancel out here. And if this was a 2, or if this, and these, there's actually fractional ones and stuff like that. But anyway, the only ones you'll have to do are whole numbers. And I'll write it on the board, but it's in the book. Two things I can put here. So that's what we found, and I put these as the units. Those were the units because it's second order. The general equation is, I don't mind giving you this on a test. That's the general equation. So if we had second order, we put a 2 in there. 2 minus 1 just gives us the L to the 1, but we don't usually write the 1 there. If that's an order, then 1 minus 2 makes that mole to the -1, and it's always -1. But if this were order 4 or 5, which I won't make you do equations like that, but you can still find out what the units are on the first order does that. And there's also, if you just wanted to see what 0th order, there is 0th order. There's a chart in the book. That's for KR. First order. Ours was second order. So if you put a 0 in for X here, this is separate from the chart. If you put a 0 in for X, you'll get this. If you put a 1 in for X, you'll get this. If you put a 2 in for X, you get what we just got. And they listed 3 as well. Then you actually have L squared, and then it goes to -2, S and -1. And it goes on. And there are fractional orders and stuff, but we won't do that. So if you apply this when order is 0, you'll get this. If you apply that equation when order is 1, you'll get this. If you apply that equation when order is 2, you'll get this. So I'll put a question like that on D2L. But when you solve for K and I say, include the units, you have to be able to do this to get units. Or you could think this way and think backwards, and it all works out, but I think it's easier to just use that little formula. All right. Let's do another one of these. K. This is the general formula. This is actually, this is the check you're learning, I think, from 12.4. Oh, if you look at the example, you notice this isn't in standard scientific notation. You could go this far. That's what they have in the book. I could say, if I ask you a question on the test, you don't have to put it in standard scientific notation unless I ask you to. Some instructors will say, from now on, after they introduce scientific notation anytime, you haven't answered it, you will put it in scientific notation. But that's silly because we don't always do that. We really don't always use scientific notation. We only use it when it's useful. So what I'll say is only if I tell you in the question, it'll be the last sentence in the question, put your answer in standard scientific notation. But truthfully, I do A, B, C, D, and E on the test. So I'm saying I might have that or I might have that. I won't have both because they're both correct. So instead of you asking for your standard scientific notation, just realize it might be in standard scientific notation. I'll leave this formula up. And that's the general rate. All right, what do they have for us? Here they only have 3 trials. C, H. Let me be consistent. I'll put the reaction right here. CH3. CHO becomes CH4 plus CO2. No coefficients. CH4, CO. All right, that's the reaction. There's only one reactant here. So what do you think that does to this? Doesn't make it 1. But we do change that. We get rid of something. Yeah. If there's only one reactant, then there's definitely not going to be 2 of these. Well, let me say this. If it's you investigate a reaction, and let's say it's a reaction that does have 2, because we definitely know it only has one of these if there's only one reactant. But let's say we got a reactant that has two things, and it's and we investigate and we find out this is 0. That equals 1. So the rate for that in that case, where A has order 1, B has order 2, you can just drop off the 2. If you had then you would just write the rate as, and so on. If you had rate, you did some work and you figured out the rate equation is then you could write the equation as you see what I did there? But you're only investigating it and looking at this because there were at least 2 reactants. If there's only one reactant, you're necessarily going to be in the form I should mention. So what's the overall rate here for this one? Overall rate?
1,
1. Overall rate here?
2.
2. Overall rate here. If you had then your rate. So what is the overall rate now? It is 0, and it's just K. So first order, a 0th order reaction will be like that. First order reaction could be like that. So that's a first order. A first order could also be like this. No, a second order can be like that, or both of those would be second order, in which case this sort of second order would be whatever this equal sign. I think this equal sign is not making sense. No, that's fine. We're just reducing it. But here the rate equals here the rate equals but both of those are second order. But anyway, if there's only one, what am I doing there? This is rate for 0th order. These are both rate second order. They're just 2 different forms of second order. Okay, but since we only have one reactant, we know this is as far as our rate equations go. And we're looking for the order, I'll just call it M. So here's what they've got. Concentration of the reactant. And here they have the rate for the reactant. It kind of doesn't matter what's here, but it's going to be a rate. They've written it like this. But just think rate. It's this rate. They've got these units up here. They also have this unit. To be proper, I should have that there. 8, 2, 4. So let's do simplify it like we did before. These are all 10 to the negative 3, so we can drop those. Negative 11, negative 11, negative 10. So this one equals, do you agree? So then if I get all these into the powers of 10, same, then I can go. And we simplify these. And now let's do it like we did before. Can we do it that way? One of these would have to stay the same. That doesn't make any sense. Maybe this still works. Let's see. We don't have to make anything drop out of the equation this time, so I guess this works. Let's do rate 1 over rate 2 equals M 1.75, 3.50 to the M. Rate 1 is 2.06. Rate 2 is 8.24. So yeah, we don't have to make anything drop out, so this still works. There is a K here. I'm kind of ignoring that because the K is a constant. What's next? Okay. 2.06 divided by 8.24. For the problems you get, these should come out with something that looks like something pretty simple. 1.75 divided by 3.50. I've got 0.5 on my calculator, but I'm going to put 1/2. So what is M? Yep. 1/2 times 1/2 is 1/4, so M equals 2. That's better than what I was trying to get y'all to do with your inspection brains last time. Okay, there's one more question. What is K? So we know now that we know M is 2, we know we can write this as rate equals K concentration of CHO to the second power. And now we just pick any one of these we want. I'm going to use the first one. If the rate is 2.06 K, concentration is, I'll put this in 1.75 squared. Now we can solve. We could square it first, or we could divide it first. I'll do 1.75 times 1.75. That's what I get after squaring it. Three significant figures. And then 2.06. So K equals 3.06 6. Oh, I forgot the powers of 10. It does matter. These were -3 and these were -11. Crap. Yeah, we got to include those. .06 times 10 to the -11 rate equals 10 -11. So that's the rate equals K. And then our concentration is 1.75 times 10 to the -8 squared. Was it 3.06? That was 3.06, wasn't it? Just do the work, Emory. .06 times 10 to the -6. It's 2.06 times 10 to the -11. It's K. Also K equals 2.06 divided by 3.06, and we had times 10 to the, move the -6 up to the top, it's +6. So 11 plus 6, -11 plus 6 is what? The 5. 10 to the -5. Move 6 to the top. All right, so what are the units? We already decided the overall order is 2. That's all we got is this. This is our rate equation. You see that the overall rate is 2? So now we're going to go two minus 1 mole, 1 minus 2, that's the -1. 2 minus 1, we have L, mole to the -1. And that should be what's in that little chart I've got. Let's double check. Second order L. Yep. So our final point is K equals, if I want to write this properly at the end, I would say K equals that with liters per mole per second. Oh, and yeah, there's always this. K equals 6.73 times 10 to the -4. -5. That should be -6, right? Make sense? All right. two reactants, so our rate equation is gonna be, at least as far as we know now, let's see, just sit right here. Just like we took the powers of 10 off here, we could take these off and have 300, 450, and 675. If it were me, I would turn that into 10, that into 10, that into 15, that into 10, that into 15, that into 10, and this into 300, 450, and 675. You see what I'm saying? All right. You want to try? Get out a piece of paper and try. This is the case where you want to use these two. When these two are the same and these two are changing, that's one of them you want to use. And then same, changing. Did I write one of these wrong? Oh, in this case, if you use 3 and 1, then you have these are the same and these changing. So you're going to want to use here 1 and 2 as a combination to solve for one of these, and you're going to use 1 and 3 as a combination to solve for the other. And remember, you're going two are the same, and these two are different, so let's use 1 and 2. Rate for 1 is 300. Rate for 2 is 450. Concentration for 1 for NO, I said I would use 10. Two. And that cancels out. These cancel. So we're finding M here for CO. You still hung up?
I don't think so.
Anybody find M or any of these yet? What'd you get?
1.
Pretty sure that's 1 over 3. Is that what this is? Or no?
2 over 3.
2 over 3. 300 divided by 450. Calculator says 0.6666, but that's 1 over 3.
Maybe 2 over 3.
Yes, 2 over 3. Two over 3. And this is 1 over 3. Now this is 2 over 3. What's the simple way to go to turn that into a fraction? 2 divided by 3 is 0.6666. Your calculator will put a 7 at the end. There's a simple way to do that. My brain's blowing up. Maybe the simplest thing to do is to go this is 3, 3, 3, 3. Calculator, put a 4 there. One fourth is 0.25. 1/5 equals 0.20. 1/6 is 1.6666. Repeating. And just do 1 through 10. If it's anything more exotic than that. What is the simple way to do this, though? Turning a fraction in, I can't remember how you do that. You might remember how to do that? I almost never work in these. I almost always work at these days. I'll figure it out if you want me to. Go over it another day. But my brain just won't do it.
What, like how to turn a fraction into just,
Yeah,
I don't know, I just put the button on the calculator.
yeah. Is there a button on the calculator? If you had 0.33333, there's a button that does that? There's a simple way to do it. I can't believe I can't figure it out. Where's the button? I don't think. decimal form, you have to figure out what fraction it is. Oh, no. If you're stuck, if you're stuck, you just do this. 300 divided by 450. Repeating. And then just do 10 divided by 15. And that also equals 0.6666. And that's still going to, we'll still be able to solve it that way. There's an easy way to go from decimal to fraction, I can't believe. I can't come up with it, but anyway. Anybody solve for the other one? What you solved for was CL. The NO dropped out, so we were solving for CL, so you found that. Anybody find the one for NO? All right, let's solve that one. Rate for 2 is 10. And 8. Now that we know the rate for this one, it's probably simpler to solve for, but let's go through this again. 15. Oh no, I needed to use 1 and 3. We used 1 and 2 because it was the same for one of them and different for the other. Now we need to use 1 and 3, so it's the same for one of them and different for another one. So we've got to use 1 and 3. So 1 and this is 10, and this is 10. And for 3, this is 15. This is 10. And that cancels out, and then we're on the NO. Rate for 1 is 300. Rate for 3 is 675. What about this? What if we did 3 times 100 is 300. 3 times 2 times 50 is 300. We factor it. 3 times 2 times 2 times 25 is 300. 3 times 2 times 2 times 5 times 5 is 300. Right? We factor the 300 into 2 times 2, no, 3 times 2 times 2 times 2 times 20 times 5 times 5. $675, that's divisible by 5. What is 675 divided by 5?
135.
What's 135 divided by 5? 27? And 27 is, what's that factor into? 3 times 8? 3 times 9? 9 factors into 3 times 3. So down here we can put 5 times 5 times 3 times 3 times 3. Now we can go 5's cancel. One of the 3's canceled. 2 times 2 times 2 is 4. 3 times 3 is 9. And if we reduce that, we get 2 over 3. Like 10 is 2 times 5, and 15 is 3 times 5. The 5 cancels. That's probably the best way to do it, is to factor everything. You remember how to factor and cancel? I don't remember how to do that. That's probably the best way to do it. 2 times 2 is 4, 3 times 3 is 9, so now n is 2.
Is it 2 times 2 times 2? Or, like, on the top, when you factor it?
2 times 2 times 2?
Yeah.
Oh,
It's supposed to be 4 though.
yeah, I messed that up. I went too fast. What was it, 300? 3 times 100, and then 100 is 2 times 50. And that's 2 times 25. Yeah. And then 5 times 5. Yeah, I had an extra 2 up there. 3 times 2 times 2 times 5 times 5. I had an extra 2 up there. That's probably the best way to do it. If these are stranger numbers like that don't work out nice and neat like these did, then I guess you have to do the fraction anyway. But if you ended up with and you got 0.666666 on your calculator. Your calculator will put a 7 at the end just to round the last one. And then you did 10 divided by 15. Oh no, that's not what this was. That was the previous one. Let me do this again and do it the other way. Instead of factoring it, we do it in the calculator. This one was 300 over 675. Is 0.444444. And then the 10 over 15 0.66666 to the m. Then you could just pull out your calculator. Obviously, it's not 1. It's not 0 because we know things vary over here. We know it's what. So you can go 0.666666 times 0.666666. Yeah, that's 0.44444435557. You see what I'm saying? You can iterate your way to the answer. So you do that squared, and if it equals a bunch of 4s, then you're good. If you had to do it cubed, maybe, to get that to equal, but you could do it either way. So if you got stranger numbers over here that you can't factor them either, like earlier we had like 9.43 and stuff like that over here. If you have stranger numbers that aren't nice and neat like that, then you're going to end up having to do it like that and kind of figure it out. The last question, what's the overall order?
3.
Yep. And they're solving for k. And we just pick one of these lines to use. Great. For the first one, let's keep them the way they are for this one. 0, 0, 3, 0, 0, k. Squared, that squared is going to be 0.010. And then the CL is, and now this times this, then we get 0.001, and then 0.00300 divided by 0.00100. I guess we're coming out to 1 for k. 1.00 for the significant figures. But what are the units? If it's 3, if the order is 3, what are the units?
Wait, so for the top part of the equation, did you square 0.10 to get 0.0?
0. 0.10 squared is 0.0. But let me do that slower. That's when I leave you behind. I just start going too fast. Rate. So that's the rate. Equals K. The NO is 0.10 squared. CL is 0.10 to the first power. If you pull out your calculator and you go 0.10 times 0.10, it's going to give you 0.01. You with me? And then this stays the same. And if you multiply those together, you just get another 0 out. I'll do it. 0.01 times 0.1 gives me 0.001. Now divide both sides by that. And maybe it's obvious, but this comes out to, no, it comes out to 3. I gotta quit going so fast. Yeah. But I'll do it by calculator. 0.003 divided by 0.001 is 3. But we've got those significant figures. We've got 3 significant figures, 3 significant figures. So I've got to put those zeros there. Okay, last question. What are the units? Put a 3 here and minus 1, you got L squared. You put a 3 here, 1 minus 3, then you got moles to the negative 2, and S to the negative 1. That equals K. All right, y'all have a good weekend. I hope that helps. For now, look at what I have online for the quiz area and make sure you're good with that. And I'll start getting kinetic stuff right there. You too.